So today's problem is problem number 12 of the MIT 2024 Integration B regular season. Very interesting problem, and that is the definite integral from x equals to 1 or to x equals to 3 of 1 plus 1. It's more of a nested fraction. 1 plus continuous over x plus dot 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 all over x plus 1 plus dot dot over x plus dot dot, and it continues on and on and on. So more of a recursive expression of this fraction. Very interesting problem, and it's exciting. So for those of us who are here for the first time here at Everyday Mathematics, what we do is we look at problems like this. We try to solve them. When we get the solution, we share it with you. Our subscribers, as always, we do thank you for the support, and please, if you do like the video, please press on the like button. Now, onto the solution of this problem. We could extract the integrand and say let u be equal to the integrand. And as you can see, this top part here is the same as u, right? And also that bottom part seems to be also equal to u. So essentially, you do have an expression like this, u being equal to 1 plus u over x plus u. And then if you multiply across both sides with x plus u, we get that ux plus u squared is equals to 1 plus u. Now what we've really done here is we've multiplied times 1 plus, x plus u here, and then this side as well, x plus u, right? That's what we've done. And so when you multiply by u, this is xu, u squared equals to this and that would cancel, and you have 1 plus u. Now you rearrange by pulling everything on the right to the left. We eventually have an expression, a quadratic expression, u squared plus x minus 1 times u minus 1 equals to 0. Now this is good. We are heading somewhere. What we do really need to extract is u in terms of x. So we have this quadratic expression, and we use the quadratic formula x squared plus bx plus c equals to 0. We know that the formula that gives us x is x equals to minus b plus minus square root of b squared minus 4ac over 2a. Now for u, the b is x minus 1 and the c is negative 1, right? Such that u, using the quadratic formula, is negative, b is negative, therefore x minus 1 plus minus b squared is x minus 1 squared minus 4ac, that means it's 4 times positive 1, which is a, and then times negative 1, which is c, and therefore we get plus 4 here. All over 2 times 1, since a is 1 here, and so we have over 2. So this is interesting, very, very interesting. We are not going to use both answers. We have minus x minus 1 plus square root of x minus 1 squared plus 4 over 2, and minus x minus 1 minus square root of x minus 1 squared plus 4 over 2. So there has to be some level of discernment here. We need to know which answer really is correct and equals to u in the interval 1 to 3. So in the interval where x is between 1 and 3, we know that since x is positive for all this domain, u must be greater than 0. And looking at this answer, there's only one option that is greater than 0, and that is negative x minus 1 plus square root of x minus 1 squared plus 4. Because at x equals to 1, x minus 1, this is 0, 0 squared plus 4 is 4, 4 square root is 2, and this x minus 1 here is 0. So we have essentially 2 over 2, so we have 1, and that increases. That decreases, but at least this answer here is greater than 0 in this interval here. So we choose this because the negative one, the minus x minus 1 minus square root of x minus 1 squared plus 4 over 2, that is negative already at the point 1. So we're choosing this, and we're going to use this to do the integration. And we've decided to plot these two values using Desmos. And as you can see, the negative one, this one here, is also negative in the interval between 1 and 3. And only this blue where there is a plus in between here is what we need. This is the one that we want to use. So we quickly go in and plug in place of these complicated nested fractions. We just plug in the integral from x equals to 1 to x equals to 3 of negative x minus 1 plus the square root of x minus 1 squared plus 4 over 2. And so you can pull out a half. And since I don't really like playing with this x minus 1 business here, I can substitute for x minus 1 with y. And so dy dx is 1, and so dy is dx. And then for limits, when x equals to 1, y is 0, and x equals to 3, y is 2. And so we just come back and plug everything in there. So we have the integral of a half negative y, and then the plus the integral plus a half times the integral from y is equal to 0 to 2 of square root of u squared plus 4. This first integral is easy because that is the same as we can first of all just differentiate these two integrals using the color coding. So we have the first one as blue, and then the second one as green. And then when we integrate negative y, it's the same as negative y squared over 2. And then we have this constant half here with the limits as applied appropriately. So we have 2 squared over 2 minus 0 squared over 2 negative negative, and that means we have half negative 4 over 2, and that's the same as negative 4 over 4, so that means it's negative 1 for the first integral. Now the second integral is what really becomes a little bit complicated, so we're going to pull it out. We can use a trigonometrical substitution if we, in place of y, we put like 2 tan squared theta plus 4. So 2 tan theta all squared. So we have 4 tan squared theta. So we can factor out 4. And we have tan squared plus 1. And that becomes sec squared theta, and then square dot sec theta. So that is one option we could do. So let y be equal to tan theta, 2 tan theta. Therefore, dy d theta is 2 sec squared theta. And so we can substitute for dy with 2 sec squared theta d theta, right? And then with the limit, when y equals to 0, 0 equals 2 tan theta, 0 divided by 2 is 0, arctangent of 0 is 0. The same with y equals to 2, 2 divided by 2 is 1, arctangent of 1 is pi over 4, so theta is pi over 4 at this upper limit. So we have 0 to 2 square integral of y squared plus 4. That is the same as from theta equals to 0 to pi over 4 of square root integral of 4 tan square theta plus 4 times, in place of dy, we have 2 sec square theta d theta, right? And so pulling out the 4 square root, that becomes 2. And so in bracket, in the square under square root sign, we have tan square theta plus 1. And then we have 2 sec square theta d theta as a substitution for dy. And then now we can now multiply this 2 and this 2 to make it 4. And we know tan square theta plus 1 is sec square theta. Square root is sec theta. So we have left with the integral of sec theta times sec square theta. let's consider this to be I so that the integral is for I here, right? So then we can go ahead and express the derivative of tan as a derivative of tan theta, right? Then using integration by parts, where if we have u, product of u capital U and product of d capital V, when you integrate that, you have uv minus the integral of capital V times d, the integral of u, right? And so v here is tan theta, sec theta is u, so that uv here will be sec theta, tan theta, minus the integral of derivative of sec theta is obviously sec theta tan theta, and times tan theta, we have sec theta tan square theta. So obviously, as we said, uv is this with the limits applied appropriately, and then the product of v du, we have sec theta tan theta times tan theta. And then we have 4 as a constant here. So this here, multiplying these two, is the same as tan squared theta, obviously. And then tan squared theta is the same as sec squared theta minus 1. And so when you plug that in, we can now get some things simplified a little bit. So we have the integral of here, sec cube theta. And since we had 4i here, so this specific part becomes, and that's why I used 4i previously, so that we can extract this out. And so keeping everything as it is and then separating this as two different integrals, and we're saying that this is I, right? And this negative and negative, this becomes positive. We can now pull this I onto this other side. So we have 4i, and multiplying this 4 times this I, we have 4i. So pushing it to the left-hand side, we have 8i. And to revert back to the 4i, we have to divide both sides by 2. So you realize that this 4 now becomes 2. And then we have that integral reducing to this. And then you can now start substituting in the limits. So sec pi over 4 tan pi over 4 minus sec 0 times 0. So sec pi over 4 is the same as 1 over cosine pi over 4. And we know pi over 4 of cosine of pi over 4 is the same as cosine of 45 degrees, which is 1 over square root of 2. Yeah. And so this is same as square root of 2. We already know that tan of pi over 4 is 1. So essentially we have 2 here, root 2, and then plus the integral. Because this goes to 0, this goes to 1, and this goes to 0. Right? So this entire thing goes to 0. And so we're left with a very interesting integral, which is the integral of sec theta. And here we're going to have to play some acrobatics, right? So sec theta is the same as 1 over cosine theta, right? And then what we can do is we can multiply the denominator and the numerator with 1 plus sine theta, right? Because when you really look at this, you can cancel this and still be left with 1. And then when you multiply this across, we have 1 plus sine theta over the product of 1 plus sine theta, cosine theta. Now 1 is the same as cosine squared theta plus sine squared theta. So when we plug that in, right, we do have cosine theta plus sine squared theta plus sine theta over 1 plus sine theta times cosine theta. Now we can factorize this part here by pulling sine theta out. And so we have here cosine square theta plus sine theta times in bracket 1 plus sine theta. Now we can separate this as two separate fractions. So we have cosine theta over 1 plus sine theta, because this cosine squared divided by cosine, the one cosine goes away. And here, as you can see, sine theta times 1 plus sine theta divided by this, so this and that will cancel, so we have sine theta plus cosine theta. Now this is very easy to integrate, right? And so this is the same as 2. We have this constant here. Since the numerator is the same as the derivative of the denominator, so we have the natural logarithm of 1 plus sine theta here. And then here, this is negative, the derivative of the denominator. Here we have negative natural logarithm of cosine theta. You can bunch these together by dividing this and combining it into one log function. And so we have 2 root 2 plus 2 log 1 divided by cosine theta is sec theta, sine theta divided by cosine theta is tan theta. And we have the limits applied appropriately. So we have 2 root 2 plus 2, applying in the limits, natural logarithm second of pi over 4 plus tan pi over 4 minus log of sec 0, sorry, here, and plus tan theta, tan 0, sorry. And so all this goes to 1, right? This goes to 1, and this goes to 0. So log of 1 is 0, so that goes to 0. This goes to 0. Okay. And then sec of pi over 4, we found it to be root 2. Tan of pi over 4 is 1. So we have 2 natural logarithm of 2 square root of 2 plus 1. And that is the value we get from integrating the square root of y squared plus 4 from 0 to 20. Right? However, we saw that our original integral is negative 1 plus a half. The integral from 0, y is equals to 0 to y equals to 2 is the square root of y squared plus 4. And we've already now determined that this part here is the same as root 2 times root 2 plus 2 times natural logarithm square root of 2 plus 1. And so this is that, and that goes, and goes. And so we're left with negative 1 plus root 2 plus natural logarithm of 2, natural logarithm square root of 2 plus 1. Rearranging it in a way that, because root 2 is greater than 1, so we have square root of 2 minus 1 plus the natural logarithm 2 plus 1. And this is the answer that was provided. It was a little bit windy. Now there's a second method that probably is a more tractable way of looking at it. I personally don't like using hyperbolic sine and cosine for these kind of things, but that could have been a shorter option. So it's all about being open-minded, being open-minded about these things. So if we take the option where we say y equals to 2 hyperbolic sine of x or sinh x, therefore dy dx is 2 cos x. That means that you can substitute for dy with 2 cos x dx, right? And then now if you have the limit 0 and 2 for y, when y is equals to 0, that means that 0 equals to 2 sinh x, and divided by 2 means that sinh x is equals to 0. Point. So, right, and that means that e to the power x plus minus e to the power negative x over 2 is that is equals to 0. That means that e x minus e negative x equals to 0, which is e to the power 2x 1 equals to 0. So e to the power 2x equals to 1, sorry, natural logarithm 2x is equals to natural logarithm of 1, which is 0, and so x is 0. So that's y. We have 0 in place of y for x, right? And then obviously when when y equals to 2, what we're doing here is we get 2 here, and 2 divided by 2 means that we have sinh or hyperbolic sine of x equals to 1, and therefore x is equals to the arc hyperbolic sine of 1, and that's what we're left with. So the limits, we devise them appropriately. So we have 0 in place of the lower limit, upper limit, arc sinh or arc hyperbolic sine of 1, and then in place of y, we have 2 hyperbolic sine of x, so that squared is 4 hyperbolic sine squared x plus 4 times 2 cos x dx. And so this, we can pull out the 2 out, square root is 2, and hyperbolic sine is squared plus 1 is the same as cos squared, square root, we have cos x. And so this is what we get, right? And it becomes easier because now we can pull out the 2 times 2, which is 4. And then we have cos squared integrated, and cos squared is the same as cos 2x plus 1 over 2. And now we can divide the 2, or we can pull the half out. So we have 2 times the integral of cos 2x plus 1. And that integrated, we have half hyperbolic sine x plus x. And we have the limits shown here properly. And then we substitute in our limits. So we have half sinh 2 hyperbolic arc hyperbolic sine of 1 minus sinh of 0 for this, and then plus sinh hyperbolic arc sinh of 1 minus 0. So obviously this and that go away. And so this is, forget this. So we have now 2 times half. This is supposed to be 2, and this is 1. Let's so that now expanded, we have let's just erase this. Okay. So we have things in the clear here. So expanding these 2, we have 2 sinh of arc sinh of 1 cos times arc sinh of 1 plus, since this goes to 0, which is this e to the power 0 minus e to the power negative 0, which is the same as 1 minus 1. So this goes to 0. And then here we have arc sinh of 1. So this goes to 1 definitely, because it's the same. It's the sinh of arc sinh of 1. So this goes to 1. Sorry, it goes to 1. I apologize. And then this and this cancel to 1. So now we are left with 1 here, and then 1 here. So we are left with now cos of hyperbolic arc hyperbolic sine of 1. And then cosh is the same as square root of 1 plus sinh squared. Then plugging this in here. So that means that now we are left with 1 here, 1 squared. So it's 1 plus 1, and that is root 2. Now, what is arc sinh of 1? So if y is equals to arc sinh of 1, right, means that y is equals to 1, and that means that e to the power x, y, sorry, minus e to the power negative 1 all over 2 is equals to 1. And so that means that e to the power y minus e equals 2. Right? So multiplied, of course, by e to the power y. So we have e to the power y squared minus 1 is equals to 2 times e to the power y. And so e to the power 2y minus e to the power y, sorry, 2 minus 1 is equals to 0. Okay. And we can erase this just so that we can get things on a clear footing. Let's erase this. Get our pen. We have e to the power 2y and e to the power y. This is 2 squared minus 1 is equals to 0. And so using the quadratic formula, e to the power y is equals to negative b, which is 2 plus, right, square root of b squared, which is 4 minus 4 times 1 times negative 1, which is another 4 plus divided by 2. So which is equals to 2 plus, this is 8. 8 is 2 times 4, so square root of 4 is 2. So we have 2 root 2 divided by 2. And this divided by this means that our e to the power y is equals to 1 plus minus, so let's say we forgot that, minus root 2. Now, the minus means that this value is negative, right? But it's not possible for e to the power y to be negative unless there is this y is an imaginary component. So y, e to the power y, therefore, has only one candidate that fits that, and that is 1 plus root 2, and therefore 1 is equals to natural logarithm of 1 plus root 2. So hyperbolic arc hyperbolic sine of 1 is the same as natural logarithm of 1 plus root 2. And so we plug that in, and that is the green integral, right? So the integral from y equals to 0 to 2 of y squared plus 4 is equals to twice the square root of 2 plus the natural logarithm of root 2 plus 1. But our original integral is negative 1, is equals to negative 1 plus the half of that green integral. So when we plug things in, we have negative 1 plus half times twice, so root 2 plus natural logarithm of 2 plus 1. So this 2 cancels. And so we are left with root 2 minus 1 plus a natural logarithm of 2 plus 1. And this is our final answer. So this has been a little bit windy, but we've shown two methods. I think the second method was an easier one if you really knew your way around hyperbolic sine and cosine. The first one was a little bit longer. So whatever really is something that you'd be comfortable with, you can go with it and so get back to the same answer. So it's been an absolute pleasure solving this problem. I really enjoyed it. I hope you also enjoy it. If you have a question or a comment, feel free to leave it in the comment section. Until next time, bye-bye.